So we have an experiment where we have a bunch of mathematical expressions which are equivalent but which are far away apart syntactically speaking. So we try to transform one expression into the other and guide the search, and we built a search algorithm that uses the neural network to guide it.
This is Romain Edelmann, a PhD student of the SC School at EPFL. Romain is making AI do math, and AI is doing well.
Compared to human, we haven't done any tests because the expressions are quite long and they look very different. For me, it's very hard to even know where to start. But we have done comparison between the informed search, so the neural network guided search, and the exhaustive search, let's say a breadth first search.
Let's rewind. It's often said that mathematics is about being a creative genius that successfully discovers new ideas. Well, I'm flattered by this idea, but at the end of the day, what we really want is a proof that some theorem is true, or that two formulas are actually equal. Now, what does it mean to prove that two formulas are equal?
To prove that two things are equal, the idea is to transform the first thing into the second using only equality-preserving transformations. For instance, in the case of Rubik's cubes, rotating a face is an equality-preserving transformation. The sequences of transformations from one thing to the other are proofs that the two things are indeed equal.
In other words, proving theorems is actually merely about searching for a valid proof within a huge set of tentative proofs. So mathematics is just a search problem. But there's a big difference between a stupid search for a valid proof and a clever one. Romain is making its AI learn to perform a clever search.
What we've seen is that we can greatly reduce the number of states we visit by a factor like 1,000 compared to BFS. But the running time are sometimes not so good because we need to feed the neural network, and which we don't need to do for BFS because it doesn't need this information. So for small examples where the distances are quite small, then the BFS is faster. But for larger examples, BFS times out because there are so many states that you cannot all visit them all. And in the case of our informed search, we are able to very effectively prune the search space to visit only the relevant nodes.
Now, that was the general idea, making the search smarter. But how can we do this? The trick is to combine state-of-the-art neural networks with the structures of mathematical expressions.
Mathematical expression can be represented as a tree. So if you have a 3 plus 2, it's maybe a tree with a node plus and a 2 and a 3 for the leaves. So there is some kind of a structure in the mathematical expressions, and we can exploit that using adequate networks.
So mathematical expressions have a tree structure, but neural networks don't know how to handle trees.
So the idea is to go from this tree structure to a vector, and for this we use a Tree-LSTM network, which is basically recursively applies an embedding, recursively builds an embedding for the entire tree based on the embedding of the subtrees.
So now our mathematical expressions are turned into vectors. Does this ring a bell? Like perhaps a previous video we did with Martin Jaggi on word vectors, which are vectors that represent words?
It's similar in the idea to word2vec, except word2vec tries to find an embedding for each token, and we are just one step later where we try to find an embedding for the entire sentence or for the entire expression. And in the case of Tree-LSTM, we are able to use a structure in the mathematical expressions to faithfully represent them.
So what is the dimension of a vector representing a mathematical formula?
For now we use 64, but this is a bit arbitrary, but it's something that we found that works well. Well, it's a trade-off between expressivity and the time it takes to learn something useful.
Now, it should be stressed that this work is just a first step.
The end goal would be to be able to apply this technique to programming languages where you have, say, two functions that maybe work differently, but you want to know that they do exactly the same thing. And the idea would be to maybe transform this first function into this second function step by step, so that we can say, oh, those are really the same function.
In other words, the end goal is program verification, that is, the ability to certify the validity of programs, which, as we've discussed it already, is a major field of research in computer science.
But this technique is not, well, I think it's widely applicable because it's not restricted to some particular domain. And
yes, because in the end, it's about making the search more clever.
The one sentence resume is that, yeah, I apply machine learning to prune the search space for search algorithms.
There are many things you can use machine learning on text, but to do that you need to transform your input data into numbers, and that you then feed into the machine learning system, for example a classifier or a neural network, and then you can use it to get a nice application.
And so verification tries to establish this correspondence between what the program is doing and what the program should be doing.